Welcome 2021ers. This is a short video to give you an overview of what Lab 01 is going to look like. This is to make up for the fact that we have extremely cold weather right now and none of the labs are meeting. This will be broken into roughly two halves. The first is just getting your environment set up so that you can work on the lab effectively, and the second half will actually go through the content. So if you're already comfortable editing text files and compiling C programs in a Unix environment, then you may as well skip ahead a bit. For the moment, just to locate the lab, you'll want to navigate to our Canvas site, click on the course materials link, and jump over here to Lab 01 where it'll be posted. There's also a link on Piazza as you go through. Keep in mind that eventually, according to the grading policy, as is the case in most labs, you'll have to submit the answers that you construct to the questions and also check off in person with a TA, either individually or as a small group. In most cases, there'll be a code pack associated with each lab, as there will be with assignments. There's a listing in most cases of what files come with it. You can download it up here from the top. I've already done that and saved it in a spot that we'll look at later. But for the moment, you'll want to maybe survey, if you're new to the Unix realm, some of your options to access a Unix environment. In a second, I'll make use of my local machine for this, but if you don't have a Unix environment set up already, consider the following options. The first is dead simple. The university provides the VOL system, which is a virtual environment that you can access through a web browser. I'm going to open this thing up in a new tab for a second and flop over here. You'll want to make use on this site of the Connect Now link. There's slight problems with the 3D version of this, and we won't be doing any 3D programming, so there's no sense in going that direction. Punch out to Connect Now, enter your University of Minnesota login stuff, X500 and associated password, and this should get you into a site that will allow you to launch new sessions. I don't know why this error message shows up all the time, but I make sure just to close out. You want to punch launch session. XFCE is a desktop environment that's there by default. You can probably set up others, but I suggest sticking with this one for the moment. Press launch, and in mere moments you'll have right there in your web browser a complete Unix environment that features a file system that's connected to your University of Minnesota Labs account. So you open the little folder guy right here. Sorry, that's the desktop little folder guy right here. You can see in my home directory, if it ever comes up, there's a whole bunch of stuff, cruft that's left over from various classes. And most importantly, if you punch the terminal here, that'll pop up and give you a terminal that has access to all the Unixy stuff. If you're unacquainted with any other text editors, I suggest Atom. You can punch that in the command line here, and eventually that'll show up. We'll demonstrate that locally in a second. So no excuses. If you have a web browser, then you have access to University of Minnesota Unix systems. There are some other options, though, and so for the moment, let's explore those. I'm going to close this tab for the moment. Make sure to log out if you're doing this at home. You can, if you have access to any sort of a terminal, then SSH into those machines. This is a secure communications protocol, SSH, and if I were, for instance, wanting to get at some lab machine, my go-to is apollo.csclabs.umn.edu. I'll make a copy of that, and I'll have to mention what my username is on that system. So it's Kaufman @ and then the machine name, SSH there. If it's your first time doing it, you may get a little message saying, is it okay to connect to this machine because it's new. Looks like we're taking a little bit of time right now, perhaps more than I would want in most respects. If a particular machine doesn't seem to be responding very much or fast enough for you, you can look at the big list of machines that comes directly from the CSCI CSCI Labs site. You can see on here a bunch of lab machines listed that you can actually go and physically sit down at, but there are also machines that are in the machine room which you can't access via anything but SSH. I'm going to give Atlas a shot here to see if it's live and kicking. Yep, okay, good. So when in doubt, I'll try something else. Punch in my password. No fear if it doesn't show up on the screen, and no worries if you get it wrong the first couple times. Eventually this will then get you a terminal, but that's it. I can list what's in here, and you'll see all the same things that would show up on Vol, but otherwise I have somewhat restricted access, so familiarity at this point with a text-based editor like VI or Nano can potentially be useful to get work done. But since we'll be working on a terminal mainly anyway, it's not a bad idea to get acquainted with some of those, although it's not the point of the class. Don't favor learning those at the expense of costing you time on assignments. Make use of whatever works, such as Atom, to get the job done. So that being said, then the other sort of bits that show up in the lab description here, you can always go sit down at physically at one of the many classrooms or public CSC labs. All of them that are on Linux are connected to the same file system, so you save your stuff on one machine, sit down at a different machine, and it'll be there. You can attempt to run some version of a virtual machine as a guest operating system if you want to give it a shot. But if you're running Mac OS X, then you already have something of a Unix environment. Just make sure to download a proper version of the compiler, GCC, via the Homebrew project. And if you're on Windows, strongly suggest the Windows subsystem for Linux on Windows 10. There's a short video tutorial linked in the lab that will take you through the steps to get a working Linux distro installed side by side with Windows, so you can basically fire up a terminal and get work done for the class done. So that will end our segment on basic orientation of getting access to those Unix systems. Once you're actually in, we're going to switch gears and walk through a few steps of just sort of navigation in a terminal. The most important command initially is to be able to change directories. So as you download code, for instance, then you would want to be able to change the directory where it's downloaded. For the moment, let me download this Lab01 code. I'm going to save it right now in, let's see, I'm just going to sort this thing by names here. I got to go to home, sorry. I'm going to save that in a directory called 2021 work for the moment. And then we're going to change screens over here to a terminal. And I'm going to make this thing big for a second. Usually when you log in, you start in your home directory. You can tell where you are located by doing a pwd, print the working directory command. This is home Kaufman. Maybe slightly different if you're on a lab machine or on your home machine, but this is fairly conventional in Unix systems. I had set up a moment ago a directory called 2021 work. The cd command will allow me to change over to that directory. Do a listing, and you can see some stuff in here. And you also note then that according to my print working directory, I'm now someplace different. If you're more accustomed to working on graphical stuff, as evidenced by that bit on Vol, you can fire up, for instance, a Nautilus file browser, and this will give you a graphical view of where you're at. I can scroll down here to 2021 work, for instance, and see the same files listed here graphically and manipulate them. For the moment, I'm just going to get rid of this directory because I'm going to recreate the magic in a second. I was expecting there to move to the trash for the moment, just to get it out of the way, although there are more severe ways. And you'll see then in the terminal, if I list, there's no longer that other folder that was in there. Instead, all that remains is the zip that I just downloaded. To unzip things on a command line, you just use the unzip command. There's also a zip command to create zips, although it's slightly more complicated, and probably prefer GUI stuff when you get to the point of needing to do that. We'll post a little guide associated with creating zips in the event that you guys are unacquainted with it. But an unzip will just recreate that directory that's in there, and I'll change over to Lab01 code. You'll notice in my terminal I have it set so that it actually lists the current directory as part of the prompt as well. There's lots of little configurations you can do like that to customize your experience and suit your tastes. If I look around in here now, you'll see a couple C files and also the eponymous questions.txt, which is going to be what you'll fill in each time you do a lab, and the answers that show up in there should be what's submitted to Canvas eventually. So at this point, now that we're sort of oriented, I'm going to show a couple of things. For instance, here is the lab that'll keep on the left-hand side, and most importantly then is a copy of questions.txt that will follow along with. Over here, I'm going to keep an editor open, and this is Atom, a nice graphical browser. From the File, Open File menu, what you should probably do is open up a copy of questions.txt, and as you figure things out in here, copy down answers in the text itself, eventually save it and upload it to Canvas. I'm just going to follow on the left-hand side in this web browser instead, and use the editor to make changes to C file and inspect the code that's in there. So for the moment, we'll follow along then with the instructions in Problem 1, which are just to invoke the compiler called GCC. And the results of this, if I call GCC on the C file age.c, if I look around in this directory again, I'll see this new file a.out, which is the default executable name when GCC runs if you don't tell it otherwise. You can usually run this program then by saying /, that means look for a program in the current directory. A.out, that is a program. I'll run this thing, and then I can start entering things like my age, 25, I wish, but no matter in that. And then I get a little output after that has been entered, a certain number of minutes old that I am. I'm able to imbibe alcohol, but I cannot be president. I can run that thing again. And actually I should start following on the lab. I'll enter 16 here to see that thing. A common technique on the command line is to use the up arrow to recall earlier commands. So I keep pressing up and I can see things, and down to move backwards. This will save me a little bit of typing as long as my terminal is in good shape. So there's 16, 18, slightly different amount. Can vote, but can legally imbibe alcohol. Let's see, here's 8, I entered 25. I guess I did that one already. And 44, imbibe alcohol, and but cannot be president. Well, that seems a little weird, but we'll go to that in just a second. So the next step then, after copying the results of that into questions.txt, would be to start looking at the code associated with the age.c to see how it works. So we'll do that up here in this browser. We're going to open a file on Atom, and here's age.c. There are faster and shorter ways to do this. For the moment, I'm going to make this thing big so we can see all of it. And actually, I'll put it over here on the left because I want to keep in mind what I'm looking for here. It says to analyze the code, look for a flaw in the conditional structure. At this point, you should be well acquainted, based on prior programming experience, with conditionals. Here's a series of them: if, then else if, then else if, then else. And what we'll want to look for is why I cannot seem to hit this. You can vote, drink, and be president. Try all three at once. That's down here. Now, an easy sort of call on this then is to analyze, okay, if it's less than 18, I end up here. If it's greater than 18 but less than 21, I end up here. And if it's greater than 21, then I'd end up in this case. If I really wanted to be able to hit this last case, then I have to put probably an additional range on here to say if it's less than some number. I can't recall off the top of my head what it is, but it's right here in the lab. Age 35 or less, you can't actually be president. So if I wanted to fix this, I'd have to plop it in, and that'll teach you just a little bit about the double ampersand. That's the logical and as it shows up in C, same as it is in Java. So I'll say less than 35. Plop this thing down here. Make sure to save this. So that's here, and keep in mind the command line or the command shortcut Control S will do it, as it is the case in most programs. I'm gonna make this thing a little bit shorter so I can see my terminal again. And then on down here, run my a.out again. I'll try 44, which should hit the last case, and find crap. This hasn't changed things at all. You see, you may imbibe alcohol but cannot be president. I thought I was going to hit this last case down here. The trouble with C programs is that changes of source file need to be recompiled to recreate the executable. If I do a listing right now, but I'll pass the -L option to see a long listing, you can see that this age.c file was very recently modified. However, the a.out that's based on it is actually older. So within the executable program, we haven't seen the change reflected in the source code. To see that, I need to recompile it. So I'll scroll back up here by pressing up a few times until I find that GCC again, recompile this thing, and see that, ooh, I have actually a syntax error. And that's because I forgot age years up here. So I'll try age years, plop that down. I'm going to Control S to save it again. And notice the little star up here disappeared to indicate that this file has actually been written to disk now. Another classic mistake, try to compile something that you haven't actually saved and you won't see any changes reflected in it. Notice this error message here. GCC is telling me a specific line number, 23 right here, where there's some sort of a syntax flaw. When I recompile at this point, you'll see none of that sort. And if I do a long listing, now my a.out is basically in sync with the C file. If I run it one last time, here's 44, and you actually see the condition that we were supposed to get. If I were trying to answer this thing, at this point I would probably take this little demo session, plop it in, and probably also paste in the lines of code that I needed changing up here. So far so good. Moving on to part C, I'll attempt to enter some strange ages. For instance, 5,000 years old. To my knowledge, there isn't anybody that's actually that old so far, but it happens. And oops, sorry, there's a minor mistake there. Here's a quick tip. In Unix terminal, if your program's running and you got to a spot you didn't want, or if it's misbehaving, press Control C. Unlike most other areas in computing these days, Control-C doesn't copy anything in a terminal. It will issue an interrupt signal, and the default behavior of most programs is to die at that point, giving you your terminal back. So I'll run a.out again, this time enter 5,000 at the prompt instead of on the command line, and you can see a peculiar result right here. You multiply 5,000 by however many seconds there are in a year. Those are two positive numbers, and you expect to get a positive result. Instead, I get something that's very, very negative in this case. And similarly so, if I run that a.auto again and enter minus 5 years old, for instance, I get a negative quantity for the minutes old. But if I enter minus 5,000, I get a positive age. This is an inkling that something weird is going on with the arithmetic. What we'll find out is that since there are a limited number of bits used to represent any given number, it has limits. And when you go off the top, it wraps around in a ring to become negative again. So multiplying two very positive numbers in this case yields a negative result. Similarly, multiplying two very negative numbers wraps around and becomes a positive number again. A phenomenon usually referred to as overflow going positive or underflow going negative. More on that later on when we talk about binary representations. So that answers part C. Let's talk about D. Describe which function is used to print information to the screen. This is going to become your best friend. So looking up here at the source code again, you run it down, and the closest thing I see is printf. A couple things to note on that. There's almost always a string argument given here, and see that's between two double quotes. You can see a \n here would carry a name down, and other invocations printf you'll see down here actually allude to the fact that this thing isn't just a plain string, it's referred to as a format string. So the %d here means substitute something in, and that will be the case with most % stuff, as in this %d means I'm going to give you one more argument, age minutes, and that should be substituted and formatted as a decimal number, thus the d. There are actually a bunch of different ways to print integers in octal, hexadecimal. I don't think printf has a binary version, but it really ought to. And there'll be differences then in sort of formatting floating point numbers as well, which will be %f in most cases. So to that end, get used to printf and start to explore some of its capabilities, as it's the primary way to get things onto the screen in C. Jumping down here, describe what function is used to read typed input interactively from the user. The only place this is read is right after prompting for the age, and you'll see in addition to printf there's a scanf function. And similar to printf, which potentially uses a format specifier to say what to print, scanf uses similar format specifiers to say what is to be read from the user. Now by default, printf will print to the screen, scanf will read typed inputs. The thing that looks slightly weird about this is that I'm mentioning here not just age years, the variable name, but an ampersand age years. And as we discussed in lecture, the ampersand is an address of operator. So this isn't passing in the value of age years, which would be 0 at this point. It's instead saying there's a memory cell associated with age years. Probably has an address like 1024 or 2048. Pass that address in. And this will allow a non-local change, that this function can actually make changes to the local variables of this other function. Normally this isn't possible, which is why in languages like Java and Python, they're usually designated input methods that would read an integer or read a string. Versus C, you can read multiple things in so long as you provide addresses associated with those. For instance, if I wanted to read 2 integers, I'd say %d here, and I'd have to say, for instance, the address of an int and declare up here somewhere an int, which doesn't have a value now, but as soon as it's read in, then it will take on the value that the user types. Now, it's a good practice to prompt each time you want something. So, for instance, enter 2 numbers here instead of 1. I'm going to undo all of that with some Control-Z's because I don't want to change the state of this program too much at this point. So this scanf function is also going to become your friend in terms of being able to read in input when needed from either user typing or potentially later on using fscanf to read from files as well. I think that takes us through the extent of the first problem. This was associated with this age.c file. And the second problem, which we'll move on to, is associated with working with these colats C files. Let's open those up quick and examine for just a second. Here's colats main. And then I'll open up also colats funcs. And if you're curious, you can also look at the header file, colats.h, which will look slightly different. Now, it's not required that you understand everything in here at this point, but some things should become apparent based on your understanding of the first problem. For instance, uses of printf and scanf to read things in here, declarations of variables, the fact that there's a main function up here. What we'll examine in the next problem is the basic compilation system that C uses. So following along here, let's compile this program using the following invocation of GCC. I'm going to make a copy of this because I don't feel like typing too much. I'm going to shrink this guy up so I can get my terminal back. In most cases, in modern terminals, you can right-click and there'll be a paste option. Happens that in my Linux terminal here, you can also press Control-Shift-V to paste things and Control-Shift-C to copy things in the event that you need to. But for more, I'm going to compile this thing. I'm going to do a listing here to look around right now. There is an a.out. Turns out that thing's older. There's a new thing on here, colats, which is now a runnable program. And if I type that in, colats, I'll follow on here, do so and enter the following inputs, starting integer of 7 and a show output of 1 so I can see it, and you'll see a bunch of stuff done along here. So this output is not going to come from main as you see it here, but it's instead going to come from some of the functions that are called in here. You'll see, for instance, this call to colats next, which gives me a variable value that I'm going to print out. You can see that up top here, the next value in the collat sequence is 22. That's coming from this printing here. And after reading in the whole verbose business, this collat steps is called, and something's printed out after it, but apparently this function prints out a bunch of other stuff, which is going to be the output that's given here. Copy this stuff up, paste it in my questions.txt, and continue examining. One of the interesting aspects of compilers is they usually have a ton of options associated with them. For example, GCC has a -o option which will slightly alter its behavior. Copying this line in, paste that on here. If I do a listing again, what you'll see is, in addition to that a.out from problem 1, the colats, which I created a moment ago, there's now a glip-glop, all in caps here. This thing, if I ask what kind of file it is in fact an executable as well. And running it, note pressing tab at this point will complete for me, saves me a lot of typing, will do exactly the same thing that colats did. For instance, I'll punch in 7 here and a 1 here and get the same output. This is an indication that this -O option actually names what the resulting program from compilation should be called. And you can name things whatever you want. We called it colats earlier. We renamed it glip-glop. That doesn't eliminate the original program. It still sits around here. Just creates essentially a duplicate of it. Finally, if I run GCC without specifying that -O option, let's see, we got that there. Then I can do a listing here, and nothing new is in town. If I do a long listing and see what's new, you'll see that this a.out here is actually the newest thing in the directory. And that's because a.out is now the default name and has been overwritten. It was that age program, and now it's this colats program instead. Behaves identically to colats and glip-glop. So in most cases, by doing this -O, you can name the resulting program whatever it is you want. Conventions are usually, if there's some main sort of program that's mentioned there, like colats main, you name the resulting program associated with that. For instance, colats or colats main. Next problem, run the following command, which attempts to compile just this one C file and name the result whatever I want. Notice up here, in the case that I compiled earlier, and the glip-glop case, and before that, I compiled 2 C files at once. So if we copy this guy over, paste it in here, you'll see an interesting error reported by GCC. There's an undefined reference to colats next. Now, looking carefully at the source code up here, I'm just going to make this big for a second, you can see that a couple of things are at stake here. There's a colats next call here to a function, but no mention of where it's defined. Instead, that's defined over here in the colats functions. Right at the top, there's this colats next guy. Now, the reason that the compiler doesn't complain that I don't know what this thing is due to the inclusion of this header file. You can see mentioned in colats.h, this function is declared. And really all the compiler needs at the early stages is there is a function that's named this. It takes an integer argument and will return an integer. And that will allow it to compile parts of this main function so that they'll be compatible with wherever that function is. It's a nice part about C programs and most other program environments is that they feature separate compilation, as I can compile this thing separate from the other C file here where those functions are defined. It allows you to create, for instance, a library of functions that many different executables can make use of. Where things go wrong is that at the point of actually creating a program, this function definition is needed. And since there was no mention on the command line during compilation of where that function is defined, the compiler flips its lid, and it's actually a linker error to say that in order to make a program, I have my main, but I do not have the other functions that are needed, for instance, colats main and colats steps, which is defined below on down here. So to that end, there are several things that can go wrong during compilation. The converse of this, explored in part D, is if I try to just compile this thing, colats funcs, I'll get an error which indicates that there's no main function. Turns out that C programs need a main function because that's where all of the action starts. It's what's referred to as the entry point. Trying to compile something to a program that doesn't have a main function will get you a lot of fuzz from the compiler. It will indicate that it needs a main function in order to create a working program. Now, there are ways around this to some extent, but they involve more sophisticated options to the compiler that we'll talk about later. And in particular, to pull off this separate compilation thing, you want to stop the compiler at the early stage, as in just convert into a low-level representation. Don't actually try to form a program yet. More on that later, but so long as you understand some basics about how to edit a program, for instance, in an editor like Atom, how to in the command line navigate to a directory and start doing some compilations and be apprised of the fact that there's some errors there, you should be in good shape as we go forwards with the lab. I'll see you all in lecture, and good luck coding.